Welcome to our lesson on the photoelectric effect. In the late 1900s, it was found that some metals used as cathodes in cathode ray tubes could be induced using only sunlight to release electrons. This was known as the photoelectric effect. Scientists tried to use the wave model to explain the observed phenomenon, but it fell short. Two puzzles arose, one involving the frequency of the incoming light, the other involving the intensity or brightness of the light. It was thought, using the wave model, that if you increased the frequency, then you would decrease the wavelength, thereby letting more wave crests hit the cathode, thereby releasing more photoelectrons, and therefore the current should be affected by the frequency of the incoming light. That's not what happened. What actually happened is that the increase in frequency caused an increase in the energy of the photoelectrons, or in other words, their speed. So if you increase the frequency, the photoelectrons that came out were faster. Well, how did that happen? And it also had been predicted that an increase in the intensity would increase the energy, but we just saw that the frequency did that. What happened with the brightness or intensity was that it actually affected the current. So we have a little bit of a confusing problem. Let's summarize what we know. We know from the table that the intensity, according to the wave model, a change in intensity would cause more energetic photoelectrons, while a change in the frequency should make more electrons escape. More electrons, higher current. Previous to this event, Max Planck had come up with an idea of quantum photons, that is, that light might consist not of a wave, but possibly particles. Each particle would have an energy that is related to its frequency. Higher frequency, higher energy. Albert Einstein took this idea and applied it to the photoelectric effect. He said that each photon with a definite frequency and energy would pass that energy on to the photoelectrons. Higher frequency would mean that the electrons would escape with more energy. Einstein also used Planck's idea to explain how the intensity could affect the current. Since each photon consists of one bundle of energy, then higher intensity light would actually contain more photons. So more photons would mean brighter light. So if you shine the light brighter, that means more photons come in, and so more photoelectrons will go out, resulting in a higher current. Even though Einstein is well known for his E is equal to mc squared, it was for explaining the photoelectric effect and validating Planck's quantum hypothesis that he received his Nobel Prize. If we look at the work that Einstein did on the photoelectric effect, we see that he established a basic formula that the maximum kinetic energy of the ejected photoelectrons comes from the energy of the incident photon. However, this incident photon energy is reduced by something called the work function. The work function is the energy required to break the electron away from its atom. You can see that EK max of the electron again is equal to HF. Now it turns out that the work function is the minimum energy required to liberate an electron, and so we say that FO is the threshold frequency, or the lowest possible frequency required. We also see there's a variation on HF when we show HC over lambda using the wavelength rather than the frequency. We'll discuss the threshold frequency and the stopping voltage later in this lesson. Each metal has its own distinct work function. The work function is a physical property. It depends on how close the atoms are and how tightly they hold on to their electrons. So different metals have different work functions. If the incoming light HF, has the same energy as is required by the work function, then the ejected photoelectron will have an energy of 0. And at that point, we say that since W is equal to the HF minimum, or we call it HFO. So FO is called the threshold frequency. At this point, we're going to show two short animations involving a lithium atom. We'll show the two inner electrons in the lowest energy level, and then there's a single electron in the outermost energy level. It's an easy atom to draw. We'll assume that it's a cathode and it's being struck by a photon of light. In both cases, the photon will come in, strike the electron, but there will be two different effects. In the first demonstration, the frequency of the incoming photon is less than the energy required to liberate the photoelectron. So the photon comes in, strikes the electron, but doesn't have enough energy, so it bounces away. And the situation doesn't change for the lithium atom. EK max is 0 because the incident frequency is less than the threshold frequency, and therefore the energy of the incoming photoelectron is less than the work function. So therefore no liberated electron. Since no electrons are liberated, the current is 0. In this second animation, we show the same lithium atom, this time bombarded with incident light where the frequency is greater than the threshold frequency required by the cathode. We can see that the photon comes in. As it comes into contact with the electron, the photon actually disappears because all of its energy is converted into energy of the photoelectron, which causes the photoelectron to have enough energy to leave the atom. That's where the photoelectric current comes from. In this case, EK max is greater than 0 because HF, the incoming photon, is greater than HFO, the required work function. So an electron is liberated and the current can be measured. The idea of stopping voltage can be shown using a simple illustration. If an electron is liberated from a lithium atom, it is then sent through an electric field. The electric field acts against the motion of the electron and therefore stops it. If we multiply the stopping voltage by the charge on the electron, we can calculate the kinetic energy of that electron. And so EK max is equal to QV stop. The reason we use EK max rather than just EK is that we are only concerned with electrons with the most kinetic energy. Those we assume would be the ones that are ejected from the surface of the cathode. Electrons that are ejected from the surface will have lots of energy. Electrons that are ejected from beneath the surface may have to fight their way out and therefore may lose some energy. We're only concerned with EK max. Thank you for attending this lesson. Please review it a number of times. After reviewing this lesson, please go to the sample exercises to look at mathematical applications of the photoelectric effect and quantum hypothesis.